In this video, our goal is to begin on page 14 of our notes. Here is a quick reminder that the question we're solving on page 14 actually continues from page 13, where we were talking about the data collected on private and public college tuition. Our goal was to see if we can predict the response variable, private college tuition, based on information provided by public college tuition. So, having collected this data, question B on page 14 here says, how much does average private college tuition increase when the average public college tuition increases by $100? In this context, this is what you need to do. You need to find the fitted simple linear regression model. To do that, let's go to StatCrunch, and I'm going to close out of this. So you have the statistics, go to regression, indicate that you want simple linear regression, click on that, choose your Y variable. That will be, we want to see if private college tuition, if it depends on the public college tuition. And we'd like to perform this hypothesis. And we're going to click on compute. So here we go. In particular, what you need here is this piece, which is the regression equation, also known as the prediction equation. So I'm going to take that here, and I have the private equals 3023 plus 2.969 times public. I've rounded off some of these regression coefficients. You're welcome to round it off to as many as MyStatLab requires, how many decimal places it requires. So please take note of that. So in particular here, we are going to draw a table of relationship. What does this 2.969 mean? Here it is. You see, I'm going to draw a table in one of the columns. This is the column for public college tuition. If it increases by $1, if this public right here increases by $1, we expect private college tuition to also increase. Why? Because the slope is positive. If the slope was negative, as public increases, private decreases. But because the slope is positive, as public increases by $1, we expect private tuition to also increase too. But by how much? By as much as the slope, which is $2.969. So back to this question. What happens then when, in particular, the average public college tuition increases by $100? Well, that will simply mean that 2.969 will increase by a multiplying factor of $100. So that'll be approximately $296.90. When you get your answer, remember to communicate in response to the question. When the public college tuition increases by $100, as we saw here, we anticipate that the expected associated increase in private college tuition is $296.90. With that said, we move on to question C of the same question. This says, when the average public college tuition reaches $6,500, that is, if you set this public tuition to, if you set 6,500 into this value, into this equation, what would be your answer for the predicted private college tuition? That is our interest here. So, having defined our interest here, we see that we can plug in 6,500 into the place of where you have public. So for this problem, we want to predict what the estimated private college tuition is when the average public college tuition reaches this value. So all we need to do is just plug in 6,500 here, which is what we're doing in this line. If you multiply these two numbers and add your answer to 3023, approximately you will get $22,321.50. That would be the predicted private college tuition when public colleges are charging $6,500. With that said, we proceed to page 15. Here we are on page 15. And for this example, we're told that a regional retailer would like to determine if the variation in average monthly store sales can in part be explained by the size of the store measured in square feet. In a nutshell, we have identified two numeric variables from this first sentence. And that is looking at the size of the store and the average monthly store sales. And we have a sample data here just for visual representation. What you immediately observe is that the average monthly sales is a numeric variable, so also is the store size. So bearing that in mind, let's read further. A random sample of 21 stores, so 21 stores, 21 rows, was selected and the store size and average monthly sales was computed. The following results are shown to the right. Question A. Compute the simple linear regression model using the sample data and use it to determine whether variation in average monthly sales can be explained by store size. In other words, does average monthly sales, does it depend on the store size? So that means average monthly sales will be our Y and the store size will be our X. So to get the simple linear regression model, this is what we do. You can use Minitab technology, or in this class, we are using StatCrunch technology. So let's go to StatCrunch. I'm going to close out of this. And in particular, I'm interested in the data set I have here. Here we are in StatCrunch, and I can see the two columns of data. This is for average monthly sales. Let me pull this, go up here so that you can see average monthly sales and line this up. We have the store size. This is our Y variable. Remember we said this is we are looking at whether the average monthly sales, which is our Y variable, if it depends on the store size, which means this is our X variable. So let's go in, we go to Stat, go to Regression, go to Simple Linear, click on that. Our Y variable in this context, remember, is the average monthly sales. So average monthly sales, and then our X is the store size. So click on that. And we would like to perform a hypothesis test and compute. So here we go. Quickly. So in this case, we see the regression equation in this context. And so we have predicted sales, this is the predicted Y, is equal to 171,206 if we're rounding off to a whole number. And you have the regression slope here. So bringing that here, we have this piece here. So we want to interpret the slope and the intercept coefficients. For the slope, that is 25.32, the number beside X. This means as the store size increases by 1 square footage, that is as X increases by 1, we expect sales to also increase. Why? The slope is positive. So we expect sales to also increase by $25.32 or $25.32 on average. That is the interpretation of the regression slope. Then for the intercept, that is the number, that is the standalone number. You have 171,206. This represents the predicted sales if you set store size to 0. So when store size is equal to 0, the predicted sales will be $171.206, or 206 rather. And what you observe is, can store size ever be 0? That won't make any sense, which is why we say that this has no real live significance or value. Question B, we are to test for the significance of the slope coefficient. As usual, as we illustrated earlier, you set up the null and the alternative hypothesis. The null will say that the slope is no different from 0, since the null hypothesis is always the hypothesis of no difference. and the alternative is that it is not equal to 0. In this case, we're to use a significance level of 0.05. So I'm going to write that down, and I'm also going to obtain my critical value using the t-distribution with n minus 2 degrees of freedom. What is my n in this case? Remember, the question said we collected data on 21 stores, so I have 21 rows of data. And so 21 minus 2, that will give me 19. So I'm using the t-distribution with 19 degrees of freedom. Okay, so I would use the t-distribution calculator to get my critical value. So let me go back in here. I'm going to put this aside and go to stats, go to calculators, go to the t-distribution. And for the t-distribution here, what's my degree of freedom? First of all, in this context or in this question, my degree of freedom is 19. And since it's a two-tailed test, 5% here, which is our alpha, breaks into 2. You have what? 2.5% or 0.025 on either side. So I need the 0.025 and 19 as parameters to set for the t calculator. So I'm going to have 19 and I have 0.025, and I will click compute the critical value, which is negative 2.09. So let's go back here. This is negative 2.093, negative on the left, positive on the right. So this cuts off what? The two tails of rejection region. And we recall the rejection rule, which is to reject the null hypothesis if the test statistic is either lesser than negative 2.093, which will cause it to be in the rejection region, or if the test statistic is greater than 2.093. So let's go to our output in StatCrunch to find the test statistic to see where it will fall relative to the critical values. So let's go back here. I'll go to slope. I have the slope here. And I would like to look at the test statistic for the slope, which is 7.078. So here we go. So 7.08. This number, which is 7.08, is definitely somewhere way bigger than 2.09. So this lies or falls in the shaded rejection region. So what we observe is that since the test statistic is greater than 2.093 and so falls in the rejection region, we're definitely going to reject the null hypothesis and conclude that if we are rejecting the null hypothesis, the slope is not nothing. It is significant. So as it stands there, that will be our conclusion. Sometimes we might be told to use the p-value method. And what you quickly observe is that for the test statistic, the p-value was very, very small, so small that it is smaller than what? 0.0001. This is simply telling you that your p-value is essentially 0. So the p-value is equal to 0.000, and it is definitely lesser than alpha. Remember, when p-value is lesser than alpha, you always reject the null hypothesis. So that is consistent with what we saw if we had used the test statistic versus the critical value. So with that said, we move on to part C. Based on the estimated regression model, what percentage of total variation in average monthly sales can be explained by the store size? To answer this question, we need a quantity called the coefficient of determination. Coefficient of determination. It tells us how much of the variation in y can be explained by variations in values of x, and that is your R square. The good news is in StatCrunch, it is automatically returned to you when you carry on simple linear regression analysis, and here you have 0.7250. If you multiply this by 100, that gives you 72.50%. So your R square, or your correlation coefficient squared, which is equal to the coefficient of determination, is 72.50%. So with that, we come to the end of the question on page 15. We proceed to another example on page 16. On page 16, we are told that the accompanying data contains a random sample of 51 customers who made purchases last quarter from an online retailer. The file contains information related to the time each customer spent viewing the online catalog and the dollar amount of purchases made. The retailer would like to analyze the sample data to determine whether a relationship exists between the time spent viewing online catalogs and the dollar amount of purchases. The data will be shown in StatCrunch. And using that data, question A, we would like to compute the regression equation based on the sample data and to interpret the regression coefficients. So let's see the data and let's see how to compute the regression coefficient, the regression equation rather. So here we go. I'm going to close this and close that. And my interest is to look at, let me move this way quickly. I would like to look at the relationship between some columns of data here. And let me move that here. Good. So you have the customer account number. That is totally not useful for us. The time in minutes spent looking at the catalog and how much the person made. It will make sense to check if purchases in dollars depends on how much time you spend using the catalog. So I'll go to regression, go to simple linear regression, and which one depends on the other? I would argue that purchases in dollars, the amount of purchases depends on time in minutes. Let's see if that is true. So my Y variable is the dependent variable, which is purchases in dollars. Does it depend on the time in minutes spent viewing the catalog? And so we're going to compute this. All right. So in particular, I need the regression equation, which is this. The sample size is 51. That's your N. And so let's go back here. So purchases, predicted purchases is equal to 89.6 plus 0.897 times the viewing time. So take note, this is your predicted Y variable in terms of your X variable. So please note that I got this equation from here. Are we good? All right, with that said, let's proceed to interpret the regression coefficients. So I have computed the regression equation. Here it is. And now I want to interpret the regression coefficients. Remember, for the slope, which is 0.897, this will be in the same units as purchases in dollars. So take note that it is positive. What does this positive slope mean? As customers' viewing time increases by 1 unit, since it is measured in minutes, I'll say increases by 1 minute, I expect on average that purchases will also increase in the dollar amount by approximately 0.89. So this should be rounded off to 0.90. So this should be about $0.90. Okay, and then for the intercept, which is 89.6, this simply represents the amount of the purchases when viewing time is 0. So if you did not view the catalog at all, viewing time equals 0. 0 times 0.89, all of this piece goes away, and you're left with the intercept equal to the purchases. So that means when viewing time is equal to 0, the average and predicted amount of purchases is equal to the intercept of $89.60. Depending on the context, this might not have any practical significance. We proceed to the next part of the question. Compute the coefficient of determination and interpret its meaning. Let's go back to StatCrunch. The coefficient of determination is your R squared. That is the sample correlation coefficient squared. And when we do that, you have 0.57666. If you multiply that by 100%, you have 57.66%. So this means that of the 100% total information you need in order to predict your Y variable, 57.66% of that amount information comes from viewing time. So viewing time provides 57.66% of the information you need to accurately predict purchases. There are other variables that account for the remaining percentage of information we need to predict purchases accurately. So this is the regular everyday interpretation of the correlation, the coefficient of determination in this context. There is a technical description if you want. We say 57.66% of the total proportion or of the proportion or percentage of total variation in purchases is explained by the variation in minutes spent viewing the catalog. So still the same question on page 17. This time on question C, we have to test the significance of the overall regression model using a significance level of 0.01. As usual, to test the significance of the overall regression model, this will be connected to the population coefficient, the population correlation coefficient rather. So this is equal to 0 and versus not equal to 0. You might observe that we have seen this before, this type of setup for significance of the overall regression model, and that was something we did much earlier in this module on page 8 here. And I showed you how to test what? Hypothesis on the population correlation coefficient. So let's go back to what we're working on. In order to test this hypothesis, the null hypothesis claiming that the population correlation coefficient is equal to 0 versus the alternative that it is not equal to 0. We are expected to test this using alpha equals 0.01. Again, we use the t-distribution with n minus 2 degrees of freedom. So what is our n in this case? Remember, we collected data on 52 customers, and it is also reported in StatCrunch. Your sample size n is equal to 51. So taking that back here, your n minus 2 is 51 minus 2, which is 49. And then the significance level of alpha, this is going to be a two-tailed test based on the nature of the alternative hypothesis. And so 0.01 divided by 2, that gives you 0.005. So that will be the size of either the lower or the upper tail. So I need the 49, and I need the size of either the lower or the upper tail, which is 0.005. I'm going to plug that in my T calculator. So go back to Stats, Calculators, go to the T calculator, and you want to key in 49 and key in 0.005 and compute. So you have the negative value here for the critical value, negative 2.679. Okay, so I'm going to take that back right here, and the negative value goes here to the left, and the positive value goes to the right. So with that said, we proceed to find the test statistic. The test statistic for this particular type of setup can be found in the F statistic this time. So what is the F test statistic? How do you find that? Still go back to StatCrunch. You'll find that this time the F test statistic is right here, 66.73. Take that back here, 66.73. Take note, from the analysis of variance table, this number is significantly bigger than what? 2.67. So it definitely lies on the extreme here, in the rejection region. Since it's in the rejection region, we're definitely going to reject the null hypothesis. So we're going to reject the null, and our conclusion will be on the alternative, which is that the overall regression model is significant. And that is our conclusion there. Part D, we're to test to determine whether the true regression slope coefficient is equal to 0. So in this case, we're testing hypothesis on the population regression slope, which we have done before. We will look at whether the slope is equal to 0 versus not equal to 0. So at what level of significance? Alpha equals 0.01 right here. Take note that if the sample data evidence leads to the rejection of the null hypothesis, it means that our slope is not equal to 0, which means that the predictor variable is a statistically significant what? Factor in determining the values or in explaining the variations in the response variable. So back to the mechanics here, you have the level of significance alpha. Then you want to find the test statistic. The test statistic will correspond to the slope in the ANOVA table. So let's go to the ANOVA table or to the parameter estimates table. And for slope, right here, excuse me, this is slope. Go to the test statistic for the slope, 8.168. So I'm going to go back here. That is my test statistic. And as it is, I would like to quickly look at also the p-value here. Remember, the p-value was also reported here. That is 0 because it's essentially so small that it's smaller than 0.001. So the p-value here is literally 0. And using the p-value approach, since the p-value is lesser than alpha, we're going to reject the null hypothesis. So if we reject this guy, which is saying that the slope is nothing, in favor of the alternative that it is not nothing, which means it is something, that means we have sufficient evidence to conclude or indicate that the true regression slope is not equal to 0. So this means that the effect of viewing time on the dollar amount of purchases is not negligible, or rather, you can say that it is statistically significant. All right, we proceed to the last example here. And this example says, one of the editors of a major publication has collected data on 30 of the best-selling cars in the United States. The data is given below. So you have curb weight versus what? Mileage, highway mileage, measured in miles per gallon. We would like to, the editor is interested in the relationship between these two variables, highway mileage and curb weight. The data has been provided. Question A, we have to develop a scatter plot for this data and to discuss what that scatter plot implies about the relationship between the two variables. You have to assume that you wish to predict highway mileage based on the vehicle curb weight. What the statement means, that is the last sentence I'm highlighting on the screen, means is that if you're predicting highway mileage, that means you want highway mileage to be your y, being predicted using the other variable, which will be your x. So let us go ahead and draw or develop a scatter plot for this data set. So this is what we do. We go into Start Crunch. I'm going to X out of this and X out of this. And I want to graph a scatter plot. And for this scatter plot, my goal is to analyze this data. Who is going to take the role of my y? Remember, the question wants me to what? To predict highway mileage. So highway mileage will be my y. So going back to Start Crunch, y will be selected as highway mileage, and the other variable is the curb weight. And then what would I like to do? I would like to overlay the scatter plot with a graph of a linear model. So compute this. Good. So we see that here, if I move my cursor, I can see the linear regression model, and I can see all the points scattered around the linear model. So based on this, let's do a little quick discussion of the overall trend that we see in the scatter plot. Based on the scatter plot obtained in StatCrunch, there appears to be a moderately strong linear negative association or relationship between highway mileage and curb weight. Question B, we're to compute the correlation coefficient for the two variables and to conduct a test to determine whether there is a linear relationship between the curb weight independent variable and the highway mileage of the automobiles. We are to set alpha to 0.05. So in this case, we need to do a correlation. We need to find the sample correlation coefficient. To do that, let's go to StatCrunch, go to Statistics, go to Summary Stats, go to Correlation. Between, click on curb weight, hold down the Control button to click on mileage. And if you want the two-sided p-value, you can also compute that. So the correlation coefficient itself is negative 0.755, and the p-value is very small, that is smaller than 0.001. Essentially, it is 0. So let's take that back. So I have the first part of this question, which is to compute the correlation coefficient that is equal to negative 0.755. So then we want to proceed to the second part of that question, which is to test to determine whether there is a linear relationship between curb weight and highway mileage. Okay, to test that significance of that linear relationship, that means we need to test hypothesis on the population correlation coefficient. So we set up the null, and on the alternative, you've seen something similar to this in the previous example right here, where we're testing the significance of the overall regression model. So back to this context, this is when it is equal to 0, you're saying that the quantity that measures linear relationship is equal to nothing. In other words, linear relationship is not existent or is not significant, versus the alternative that it is not nothing, that is, it is something, and so it is significant. So we want to go on to step 2. As usual, we use our t distribution with n minus 2 degrees of freedom. What is our n here? If we go back here, data was collected on 30 cars. So n equals 30 minus 2, 28. We need to sketch our t distribution. And for the t distribution, we are working with alpha equals 0.05. For the two tails, 0.05 divided by 2, that gives you 2.5% on either side. So we're going to need the degree of freedom 28 and the size of one of the tails, 0.025, in order to get the critical value from the t distribution. So let's go back. Let's go to Stats. Let's go to Calculators. Let's go to the t distribution. And I'd like to specify my degree of freedom. Degree of freedom, again, is 28 versus 0.025. So degree of freedom, 28. Specify, I'm going to erase this and specify the size, 0.025, and compute. So this is the critical value on the left. The positive value of this will be on the right. So let's go back. So this is what I have, negative 2.0484 on the left and the positive value on the right. For this, as we have illustrated previously, we go on to the test statistic, and that will be done using this formula. And if you plug in your R value, which is negative 0.755 right here, and the same R value here, n minus 2 is 28 right here, we get negative 6.0926. And so, where does this value, negative 6.09, where does it fall? You agree with me that it falls somewhere far in the rejection region. So the test statistic of negative 6.0926 is lesser than negative 2.0484. That means it falls in the rejection region. So we're going to reject the null hypothesis. So we say that if we're rejecting the null hypothesis, it means we have sufficient evidence in favor of the alternative hypothesis, which is saying that the linear relationship is statistically significant. With that said, let us see what we have on page 19. Still the same question, but this time we're required to compute the linear regression equation and to also what? to compute the linear regression equation and to provide an estimate of the average highway mileage that you expect from a vehicle that weighs 4,012 pounds. So, in this context, how do we get the linear regression equation? You can use the Minitab technology, but we're using StatCrunch technology in this class. So let's go on to do that. So I'm going to X out of this. I'm going to X out of this and go to statistics again. Go to regression, simple linear regression. My Y variable in this case, again, is highway mileage, and my X variable is a cob weight. Make sure you choose the perform, and I would like to compute this. Okay, so in computing this, what do I have? I have the regression equation here. I'm going to take that into my working bench. Here it is. So the hat here means the predicted highway mileage based on the sample data is given by this. All right. So so as far as the first part of the question is, the green part, here is the correct answer. The next part is the yellow highlighted part of the question. That is to obtain an estimate of the highway mileage expected when the cob weight is 4,012 pounds. We're going to plug 4,012 in for the cob weight in the simple linear regression model. And so if we plug that in, so cob weight, set it to 4,012. And so we multiply that by this value, and the result we subtract it from 4717. That will give about what? 22.2113. So the predicted highway mileage for a car that weighs what? 4,012 pounds is about 22 miles per gallon. That brings us to the end of this module or